Hey, good morning, dear students. This morning we shall continue with polynomial and rational function sketching and more applications of optimization and partial derivatives. So to end up all about differential calculus. This means then finding the critical numbers and critical points, deciding which among the critical points gives a max or a min. Okay, so if you could recall, the critical points or critical numbers are obtained by taking the first derivative of a function given or a given function, or identifying that x value that will make the first derivative undefined. That gives the critical numbers. And then critical values, we simply evaluate the original function at the critical numbers and then apply either the first derivative test or the second derivative test to determine which among them gives a max and which among the values will give a min. Remember that if f double prime of c is negative, if f double prime of c is a negative, then the graph, or should I say, there is a max, the graph concaves down kasi max siya. And if f double prime of c is a positive, okay, the graph concaves upward. So there is a minimum. So we shall combine all this information plus your knowledge about asymptotes and x and y intercepts to sketch polynomial and rational functions. Okay, so let's begin with identification of the steps. So let's enumerate the steps first. Drawing the graph of a function. Okay, number 1, determine the domain. Okay, set of all possible x values. And then number 2, locate the x and the y intercepts. So we also have to determine at which point will the graph cross the x-axis and at which point will the graph intersect the y-axis. So that's determining the x and y intercepts. Then number 3, to identify the asymptotes, okay, particularly the horizontal asymptote, we evaluate the limit of the function at infinity. So remember your limit theorems at infinity, or as x approaches positive and negative infinity. So we look into the limit of the function as x approaches infinity. Now, if the limit is a number L, then y equals L is a horizontal asymptote. Okay? Horizontal asymptote. If either of this is, okay, infinity or negative infinity, determine whether f has an oblique asymptote. Okay? If f is a rational function such that f of x is equal to p of x over q of x. By the way, when we speak of a rational function, rational from the term rational, remember rational numbers, a rational number is defined as the quotient of two, okay? Two integers, yes? Quotient of two integers, or it takes the form a over b or q of p over q. So in like manner, a rational function is a function that takes the form p of x, okay, p of x over q of x. But the degree of the numerator is greater than the degree of the denominator. Sorry, this is supposed to be r. Then f can be written as, we can break it apart, or should I say simplify it as f of x is equal to g of x plus r of x over q of x. If only when the degree of the numerator is greater than the degree of the denominator, we can express it in this manner. Okay? So if this is the case, then the rational function has an oblique asymptote. Okay? Not horizontal, not vertical, but oblique. An oblique asymptote. And what particularly is the asymptote? It's the function g of x. Okay, the linear function g of x is an oblique asymptote of the rational function. Okay, number 4. So, recall number 1, determine the domain. Okay, what values of x? Number 2, x and y intercepts. Number 3, okay, the horizontal asymptote. How do we get the horizontal asymptote? Evaluate the limit of the function at infinity. Number 4, determine whether f has any vertical asymptotes. Okay? Vertical asymptotes. Is there a value of x that will make the function undefined? Now, for a rational function, particularly pay attention to the denominator. Okay? What is the zero of the denominator? That will give the asymptote, vertical asymptote. Number 5, we calculate f prime, the first derivative. And just like what we did in the previous meeting, find the critical points, determine the intervals, where f is increasing, where f is decreasing. When is it increasing, decreasing once again? F prime of x, if f prime of x is greater than 0, review. First step is identify the domain. Second step, x and y intercepts. Number 3, evaluate the limit at infinity. Number 4, determine the vertical asymptote. Number 3, why do we have to evaluate the limits at infinity? To determine the horizontal asymptote. Number 4, determine the vertical asymptote. For a rational function, just look into the zero of the denominator. Okay? A zero of the denominator or value of x that will make the denominator 0. Number 5, calculate f prime to check on or to identify the critical points. And then the intervals at which the function is increasing, decreasing. Remember, the first derivative test says if f prime of x is greater than 0, the function is increasing. Okay? Because the slope of the tangent line is positive. But if f prime of x is less than 0 or negative, the function is decreasing. Now, how about your f double prime? That's number 6. Calculate f double prime. Determine the intervals where f is concave up. When is it concave up? Concave up. This one. Concave up means there is a min. If f double prime, let me write that down. If f double prime of x is less than 0, this is concave down. If f double prime of x is greater than 0, then concave up. Oh, baligtad. Wait. Okay, if it is negative, it's a max. Correct. It's concave down. So, yan, concave downward. So, it's a max. And if it's greater than 0, it's a min. So, it would be like this. Okay? This is downward. It's a max. And upward, it's a min. Okay, so your number 6. That's number 6. Determine f double prime. Determine the intervals where f is concave up and where is f is concave down. Use this to determine whether f has any inflection points. Okay, inflection point. What is this? What about the inflection point? It's the value of x at which the second derivative is 0. Okay, inflection point. The second derivative, okay, is an alternate means to determine or verify whether the function has a local extremum at a critical point. So let's illustrate the use of these steps in example number 1. Okay. May we proceed to example number 1. Sketch the graph of the function f of x is equal to x minus 1 squared minus, the quantity rather, x minus 1 squared times x minus 2. Okay? Looking at the form of the function, what kind of function is it? Is it rational or polynomial? Is it a rational function or a polynomial function? Take note that we can expand this. Yes? This could be expanded and then multiplied to x minus 2. Then the resulting function will be cubic. Yes, because this will be x squared multiplied by x is x to the third power. So example number 1 is polynomial. Okay, so the first example is polynomial function. Okay, it's a polynomial function. So, okay, following the 6 steps that we have just enumerated, number 1, the domain, okay, the domain of this function is the set of real numbers. Any number, okay? Any number in the set of real numbers could be x. Next, find the x and y intercepts. Okay? Finding the x and y intercepts. What is the x-intercept, by the way? X-intercept, the value of x at which the function intersect the x-axis. Okay? X-axis. And what do you know about all points located along the x-axis? Every point, for example, let me label this as A, let me choose this as C. You know that this is, okay, A0, yes, and this is also C0. So what have you noticed with the second, okay, coordinates of the points along the x-axis? All points along the x-axis, all points along the x-axis have 0 as their second coordinate. So to solve for the x-intercept then, we simply let y be 0. Okay? So solve for x and y intercepts. Okay, so for x-intercept, let y be 0. And for y-intercept, we let x be 0. Okay, if it has a y-intercept. Okay, I think this is easier than the previous. Ito na lang muna tayo. The function given is f of x is equal to the quantity x minus 1 squared times x plus 2. Okay. So if x is 0, then y will be equal to 0. Okay, erase siya. 0 minus 1 squared times 0 plus 2. What will this be? 2. Okay? Y equal to 2. So, the graph surely will cross at the point, which point? x0 and y2. Okay? 0, 2. Now, how about the x-intercept? So, solve. For the x-intercept, we simply equate the function to 0, x minus 1 squared times x plus 2 is equal to 0. Okay? So, this one will give two values. Okay? This will give two values. By zero product property, we can have x minus 1 squared equal to 0. Okay? And then, The other will be x plus 2 equal to 0. Why can we equate the two factors to 0? By the zero product property. In fact, you can express this in factored form as x minus 1 times x minus 1 times x plus 2 is equal to 0. But the first two factors, yes, the first two factors will give the same x value. Okay? So, x minus 1 equal to 0 and the other will be x plus 2 equal to 0. The first x value will be positive 1 and the second x value is negative 2. So, we now have the point at which the graph crosses the x-axis. The first point is negative 2, 0 and the other point is 1, 0. So now we have three initial points. We know that the graph will intersect the x-axis at negative 2, 0, 1, 0, and 0, 2. That's along the y-axis. Now we proceed to step number 2. Number 3 rather. Take note that this is step number 2. We now move on to step number 3. What did we say about step number 3? Okay, number 3. Evaluate the limit at infinity. Okay, evaluate the limit of the function as x approaches infinity. Okay. Now, since our function is polynomial function, limit of limit of the function x minus 1 squared times x plus 2 as x approaches infinity, okay, what is it equal to? Infinity, we think of infinity as a very large number. So here, if you have a very large number plus 2 multiplied to very large number minus 1 squared, get the product, what will it be? Okay, what will it be? It's infinity, yes? Whether it's positive infinity or negative infinity, it's infinity. This is polynomial. Therefore, this polynomial function has no horizontal asymptote. Okay? No horizontal asymptote. So let me write that here. It has no horizontal asymptote because true enough, for any polynomial function, the graph is continuous. There are no breaks in between. There are no gaps. Just like your quadratic function, your cubic function. Okay? So, no horizontal asymptote. Okay, no horizontal asymptote. And at the same time, number 4, we proceed to number 4. Number 4, no vertical asymptote. No vertical asymptote. Okay, vertical asymptote for rational function is the 0 of the denominator. And since this is polynomial, tuloy-tuloy, walang gaps, walang breaks in between, there is no horizontal or no vertical asymptote, both. No horizontal, no vertical asymptote. And recall also from algebra that a polynomial of degree n, this is a third degree, has at most or will cross the x-axis at most n points. So, how many crossing points or intercepts did we solve? X-intercepts, we found 2 x-intercepts. So, tama lang, at most n. At most n means n or less. Okay? Let me write that so you won't forget. This is from algebra. Note that a polynomial function, function of degree n has at most or degree n crosses or intersects the x-axis in at most n points. Okay? So, n or less. So, in this case, we found out 2 points of intersection along the x-axis. 2 x-intercepts. And a polynomial function p of x is a function that takes the form a sub n x raised to n plus a sub n minus 1 x raised to n, okay, minus 1 until a sub 0. Okay, or may we include the last two terms in the expansion. So, plus a sub 1, x sub 1 plus a sub 0. Okay, where n are integers. Okay, n are integers, positive integers. So, if degree is 1, linear. Yes, degree 2, quadratic. Degree 3 is cubic. Degree 4, quartic. Okay, and degree 5, quintic, and so on and so forth. Number 5. So, we're ready to move on to step number 5. What are we to do for step number 5? Find f prime. Okay, calculate or solve for f prime. Find f prime, critical numbers, critical points, okay, intervals, where f is increasing or decreasing. Okay? Increasing or decreasing using the first derivative. Okay, so let's first identify the critical numbers. So let's get f prime of x. What is f prime of x? Now go back to the function given. Let me just write it here. The function given is f of x equals the quantity x minus 1 squared times x plus 2. Now, it would be easier if we multiply this. Let's expand this first. Equals x squared minus 2x plus 1 times x plus 2. Okay? F of x equal to x cubed minus 2x squared, okay, plus x plus 2x squared, okay, minus 4x plus 2. So, when simplified, f of x then is equal to x cubed, okay, these two will cancel out, negative 2x squared and positive 2x squared, leaving minus 3x, correct, minus 3x plus 2. This is simpler. Okay, so our f prime of x, now we are to differentiate this. The first derivative will be 3x squared minus 3. Correct? 3x squared minus 3. So after differentiating the function, we are ready to get or identify the critical value or a critical point, I should say. The critical point is obtained by setting the first derivative to 0. So 0 is equal to 3x squared minus 3. Okay? Or x squared equals 1. And extracting the square root of both sides will end up with positive negative 1. Okay? This is after extracting the root of both sides. So, how many critical numbers did we get? We have positive 1 and negative 1. So, may we proceed to identifying our intervals. Okay? So, critical numbers. The critical numbers that we have obtained are -1 and +1. So, let's divide the interval -infinity to +infinity using this, okay, our critical numbers. So, we'll have one interval will be x, ba't nag-e-erase? X less than -1. The other interval will be from -1 to 1. And the other interval will be from +1 to the right, x greater than 1. So this is the same as the interval -infinity to -1. This interval from -1 to 1, we will select a test point. And this interval is the same as 1 to +infinity. Okay, so we have divided it into 3 intervals. Now, I want you to choose a test point. Okay, test point, a number which belongs to the interval. Choose, okay, a test point. Okay, so for the first interval, let me copy once again. The first interval, -infinity to -1, let's choose, or let x be equal to -2. Okay, how about the interval -1 to 1? Okay, let me choose 0. Okay, 0 belongs to the interval? Yes. How about from 1 to +infinity? Let x be equal to 2. Okay, now we will use these values as our test point. Applying the first derivative test, what is f prime of -2? Okay, f prime of -2. Remember once again our f prime a while ago. Note that f prime of x is equal to 3x squared minus 3. Okay, let's go back. There we have f prime of x is 3x squared minus 3. Okay, so I just copied that. Let me enclose it. So, f prime of -2 then is equal to 3 times -2 equals 3 times -2 squared minus 3. And what is this equal to? 9. Yes? Okay. And what did we say? If f prime of x is greater than 0, it's positive. 9 is greater than 0, then conclusion, what can you conclude? Okay, conclusion, it's increasing. So from -1 to infinity, the function is increasing. Now we proceed to the next test value, which is 0. What is f prime of 0? Okay, what is it equal to? So 3 times 0 squared minus 3 equals -3. And what did we say? If f double prime, or if f prime rather, is less than 0, then the function is decreasing within the interval, okay, -1 to +1. We proceed to the next test value, which is 2. What is f prime of 2? Okay, what is it equal to? F prime of 2 is 3 times 2 squared minus 3, which is 12 minus 3 is equal to 9. Also positive. Okay, 9 is greater than 0, therefore the function is increasing. Okay? Or we can now tabulate. So that's it. From where did we get this? From where did we get -infinity to 1? Here. To the left of -1. Remember, we have two critical values, 1 and -1. Get a value to the left of -1. And then, to its right, or between the interval, negative 1 to 1, and then to the right of 1. Okay? So, these are the conclusions. So, decreasing from negative infinity to negative 1, increasing, I should say, from negative 1 to positive 1, decreasing, and from 1 to infinity, it's increasing. So, now we can move on to step number 6. Okay, step number 6. Or prior to step number 6, what can you say? Okay, so from this table that we have generated, we see that the function f has a local maximum at x equal to local max at x equal to negative 1. Local max dito at x equal to negative 1 and a local minimum at x equal to positive, okay, positive 1. So, evaluating f of x at those 2 points, we find the local maximum value. So, we did not evaluate yet. So, if we get f of negative 1 and f of 1, what will this be? Okay, our function is x minus 1 squared. So, x, negative 1 minus 1 squared times negative 1 plus 2. Here, okay, 1 minus 1 squared times negative 1 plus 2. Okay, what is this equal to? Okay, what is it equal to? This one is negative 2, 4, correct? This is 4, correct? Because negative, because this is negative 2 squared, positive 4. And f of 1 is 0. So, therefore, this is the local max, and this one is the local min. Now, we proceed to step number 6. Step number 6, find f double prime. Okay? F double prime of x. And then, we set the double prime, f double prime to 0 to see if there is an inflection point or to check whether the function will concave up or down. Again, look for intervals. Okay, so f double prime of x is equal to, again, our f prime of x equals 3x squared minus 3. So, f prime of x then is 6x, okay, or 6x only. So, equate this to 0. The second derivative is 0 at which value? Okay, the second derivative is 0 at x equal to 0. 6x equal to 0, x equal to 0. So, therefore, to determine the concavity of f, we divide the interval negative infinity to positive infinity into smaller intervals. So, we look at the value to the left of 0 and to the right of 0. So, our intervals will be, okay, from negative infinity to 0, and the other interval will be 0 to positive infinity. Okay, so these are our intervals. Let me write them once again. Our intervals are negative infinity to 0. How did we identify this? First, we calculated f double prime and then set it to 0. Okay, and then solve for x. And then identify values to the left of that x value and to the right of that x value, or from negative infinity to that x value and x value to positive infinity. Okay, so the other interval will be 0 to positive infinity. And then we identify test points. Okay, give me an x value which is found in this interval. Let's say negative 1. And how about the interval 0 to infinity? I will get positive 1. So now we apply the second derivative. In the previous step, what did we use? Look, we used the first derivative. First derivative, first derivative, first derivative to determine whether the function will be increasing, decreasing, increasing. This time, for number 6, we apply the second derivative test. So we take the second derivative, evaluate the second derivative at the test points that we have identified. So let's look into the sign of f prime prime of x. So beginning with f prime prime of negative 1. Okay, so f double prime of negative 1 is 6 times negative 1, which is negative 6. So what will be our conclusion? Okay, remember f double prime? Note, let me write this here again, once again, note. If f double prime of x is less than 0, the graph concaves down. Okay? So, maximum siya. Ganun, pa ganun. Ganun sabi ko sana. Okay? Concaves down. If f double prime of x is greater than 0, the graph this time, minimum siya. It concaves upward. Concaves upward. Okay, so going back. F double prime of negative 1 is negative 6. So what can you say? F is concave down. Okay, concave down. Now we proceed to the next test value, which is 1. What is f double prime of 1? 6 times 1 is equal to 6, positive 6. So, what is our conclusion? F is concave. Okay, concave din. Okay, so going back to our previous step, we said that the function has a max at x equal to 1. Okay, this is the maximum, local maximum value, where at x equal to 1. Therefore, let's see if it jibes with our observation in the next step. Okay, so note that in step 5, we found that f has a local maximum at x equal to 1 and the local minimum at x equal to 1. Okay, it has a local max at x equal to 1, local min at x equal to 1. F prime of x is equal to 0 at those points. Then f prime of x or f double prime changes sign only at x equal to 0. So, what is the significance of this x equal to 0? Should I say the second derivative changes its sign at x equal to 0. This must be an inflection point. So this one confirms our result in step number 6 about the concavity of the function. So at x equal to negative 1, 0, negative 1. At x equal to negative 1, what did we say? The function has a local max. Tama, concave down. And at x equal to positive 1, the graph concaves upward. It's a local minimum. So let's combine all the information that we have now to sketch the graph. So how would the graph look like? Okay, so let's draw our Cartesian plane. Okay, and label it as 0 are the intercepts, and then 0 to y-intercept, local max that we have identified in our step number 5 is 1, negative 1, 4, negative 1, 4, and the local minimum that we have identified is 1, 0. Okay, 1, 0. This is exactly the same as one of the intercepts. And from step number 6, we found out that at x equal to 0, or along the y-axis, okay, the derivative, second derivative changes its sign. So if we now try to graph, connect the points now, the graph would look like this. Okay, so this is the graph. The graph would look like that. Really, negative 1 to 4 is a local maximum and 0, 1, 0 is a local minimum. You can verify that using GeoGebra. Okay, your GeoGebra looks like this. Along the left side, you have input. Type in the function y is equal to, okay, the function is x minus 1 squared, x minus 1 squared, wait, x minus 1 squared times x plus 2. Okay? And so look at the graph. X plus 2, sorry. Let me, x plus 2. Those who have GeoGebra with them, please do the same. And you'll find that the graph really looks like this. Okay, compare it to the graph that we have generated a while ago manually. So the graph would look like this. So if you have your GeoGebra, you try to graph it too using that app, and you'll find out that you'll end up with the same graph. Okay, same graph that we have generated a while ago. So really, the function has a local maximum at the point, C, extremum. Okay, extremum, this is the extremum, negative 1, 4, correct? And the another root extremum or local minimum, which is 1, 0. Okay, now we proceed to the next. We move on to the next problem. So are there questions here? Number 1, domain, then x and y intercept. Number 2, horizontal asymptote. Number 4, vertical asymptote. Please take note, for any polynomial function, there are no horizontal and vertical asymptotes. Okay, for any polynomial functions. Okay, next we proceed to problem number 2. So the graph would look like this. That would be the final answer. Next, number 2. How about a rational function? Sketch the rational function f of x is equal to x squared all over 1 minus x squared. Okay? X squared all over 1 minus x squared. Let's follow the steps. Number 1, step number 1, find the domain of the function. So looking at the function given, it has a numerator, it has a denominator, it must be rational. Okay, it's a rational function. And what can you say? Degree of the numerator equals degree of the denominator. Okay? Now, what's the domain of this function? Obviously, the function is not defined at x equal to 1 and negative 1. Okay? Because the denominator, I should say, 1 minus x squared becomes 0 the moment x is positive 1 and negative 1. Therefore, we say that the domain is all real numbers except 1 and negative 1. So, technique is check the denominator. Okay? Find the value of x that will make the denominator 0. What are those values? 1 and negative 1. So the domain of the function is all real numbers except those two values, 1 and negative 1. Okay, so step number 2, I hope this is clear, so we can proceed to step number 2. Find the intercepts, x and y intercepts. So y-intercept is obtained by setting x to 0. So if x is 0, then what will y be? Y will be 0 squared over 1 minus 0 squared. Y is equal to, what is y equal to? 0. Okay? So, what point can we generate from here? 0, 0. So, the graph will pass through the point 0, 0. How about x-intercept? Meron ba siyang x-intercept? X-intercept, let y be 0. Will will ever be 0? Ito rin siya, 0, 0. Okay, if x is 0, then y is 0 also. Next, we now move on to step number 3. Ito rin, parehong value kasi siya because if we let x intercept, we let y be 0, then x squared over 1 minus x squared equal to 0, you'll end up with x equal to 0 also. So the same point is generated, 0, 0. Okay, 0, 0. We now proceed to step number 3. Step number 3, evaluate the limit. Evaluate the limit of the function as x approaches infinity. Okay? So, please recall your theorems on limits at infinity. If the degree of the numerator and degree of the denominator are the same, what did we say? How do we evaluate? Okay? How do we evaluate the limit of that function? It's the quotient of the leading coefficients. Leading coefficients. So, going back to our function, limit of x squared all over 1 minus x squared as x approaches infinity. The rule is, isn't it that the rule says we divide by the highest power of x? So this one becomes limit of, in fact, x squared over x squared all over 1 over x squared minus x squared over x squared as x approaches infinity, which is equal to the limit of 1 over, the limit of 1 over x squared minus 1 as x approaches infinity. Which when simplified, when you evaluate, limit of a constant is the constant itself over limit of 1, limit of 1 over x squared. What happens to this ratio? If this gets bigger and bigger, raise it to the second power, 1 over a very big number is 0. Yes? 1 over a very big number, 1 over 99 is 0.1 over 100 is 0.01, 1 over 1000 is equal to 0.00, and so on. So that when this is too large, then its limit, its value, I should say, the value of 1 over x squared is very close to 0. This is why we say limit of 1 over x raised to n as x approaches infinity is 0. So 0 minus 1. 0 minus 1 equals negative 1. So the limit is equal to negative 1. Therefore, in this case, there is a horizontal asymptote. And the horizontal asymptote is y equal to negative 1. Horizontal. A horizontal line has the equation y equal to k. Please do not forget that. Y equal to k. Therefore, there is a horizontal asymptote at y equal to negative 1. Where did we get this? From the limit. Okay, after evaluating the limit of the function at infinity, we found out that its limit is negative 1. Y equal to negative 1, therefore, is a horizontal asymptote. Okay, now we proceed to step number 4. How about the vertical asymptotes? Okay, how do we determine the vertical asymptotes? First, we have to check whether the denominator has any zeros. Okay, so going back to our function, f of x is equal to x squared all over 1 minus x squared. What did it say here? We check whether the denominator has any zeros. So let's get the denominator, which is 1 minus x squared, and set it to 0. 1 equal to x squared gives positive negative 1 as x value. Yes? So here we have then two values that will make the denominator 0. They are positive 1 and negative 1. Okay. X equal to negative 1 and x equal to positive 1 are the vertical asymptotes. Okay, the vertical asymptotes. Take note that a vertical line is given by the equation x is equal to k. A horizontal line is y equal to k, and a vertical line is x equal to k. Okay, so there are two vertical asymptotes, meaning the graph will never cross these two lines, x equal to negative 1 and x equal to 1. In like manner, the graph also will never intersect the line y equal to negative 1. So can you visualize that? X equal to negative 1 is this line, and then x equal to 1, and then y equal to negative 1. It will not cross those lines. So how will the graph look like? Okay, so we proceed then to step number 5. We move on to step number 5. We now differentiate the function. Okay, differentiate the function and determine the intervals. Choose test points, and then we will decide which one is a max, if there are max or min. Okay, so f prime of x is equal to, okay, the function is, let me write once again, the function given is f of x is equal to x squared all over 1 minus x squared. Okay, so what will f prime be? This is a quotient. So applying quotient rule, 1 minus x squared times 2x minus x squared times negative 2x. Derivative of the denominator all over the square of the denominator, which is 1 minus x squared. So let's simplify further. What will this be? 2x minus 2x cubed minus x squared plus 2x cubed. Okay? What will this be? This one will cancel out. Where did I get this? Sorry, this is not part of it. Ito wala. Once more, 2x minus 2x cubed plus 2x cubed. All over the quantity 1 minus x squared raised to the second power. Once more, denominator times derivative of the numerator minus numerator times derivative of the denominator over the square of the denominator. But when simplified, f prime now will be, f prime of x will be equal to 2x all over 1 minus x squared raised to the second power. So where are the critical points, critical values? Again, remember, critical values are x values that will make the first derivative 0 or that will make the first derivative undefined. Okay, so can you identify the critical points now? So let's first equate it to 0. F, erase. So 2x all over 1 minus x squared equal to 0. 2x will be 0, x is equal to 0. This is one critical number. Okay? So one critical number, however, this is not the only critical number that we have. Because remember, from our definition of a critical number, it also refers to the value of x that will make the first derivative undefined. Look at your first derivative. Its denominator is 1 minus x squared. So there are two more x values that will make this 0. And what are they? X equals -1 and +1. Okay? So we have 3 values. So if we try to locate these points along the x-axis, we have x equal to 0, x equal to 1, x equal to that is supposed to be -1. Okay, x equal to -1 and x equal to, okay, 0. Okay, so -1. So how many intervals can we set from here? One possible interval would be to the left of -1. That means from negative infinity to -1. Another interval would be between -1 to 0. Okay, so next interval would be -1 to 0. Another interval would be from 0 to 1. And another interval would be 1 to +infinity. How did we identify our intervals? From our critical numbers. Okay, so your critical numbers are -1, 0, 1. So if we plot this along the x-axis, it would look like this. So let's identify to the left of this, ito. Okay, -infinity to -1. And then between the two, there it is, -1, 0, and then 0 to 1, and finally, -1 to infinity. So how many test points are we going to choose? Also, 4 din, because we have 4 intervals. Okay, so our intervals are, walang space, kaya dito muna tayo. Okay, let's copy our intervals. Our intervals a while ago are -infinity to -1, -1, 0, and then 0, 1, then 1 to +infinity. Now we are ready to identify test points. Okay, test points. Give me a value to the left of -1, say -2. From -1 to 0, let's say -1/2. From 0 to 1, let's say +1/2. And 1 to infinity, let's say +2. Okay? Now, we move on to the next. What should we do next? Okay, for step number 5, we will now determine the sign of f prime of x. Okay? And then after that, we will make our conclusion. Whether it's increasing, decreasing, or, okay, f prime of x. So, once again, our f prime of x from our previous step is equal to, can you remember, 2x all over 1 minus x squared. Okay, 2x over 1 minus x squared. So, what is f prime of -2? So, let's show our solution here. F prime of -2 is simply 2 times -2 all over 1 minus, okay, negative Okay, once more, 2 times negative 2 all over 1 minus negative 2 squared. This is negative 4 all over, okay, 1 minus negative, that's negative over 9. Yeah, negative. So the sign is, it's negative 4 over 9. So what did we say? If it's negative, then it must be decreasing. How about f of negative 1 half? F prime of negative 1 half, what will this be? 2 times negative 1 half all over, okay, the quantity 1 minus negative 1 half squared. Am I right here? 3 squared, okay. What will this be? Negative 1 all over, okay, this is 1/4, 3/4. 1 minus 1/4 squared. When simplified, will be 1 over 9 over 4 or negative 4. Let me wait. Okay, so this will be 3/4 squared equal to negative 16, correct? Negative 16 over 3. Negative 16 over 3, so f prime of negative 1 half is equal to negative 16 over 3, so decreasing. Next, how about f prime of 1 half? F prime of 1 half, what will it be? 2 times 1 half all over, can you still see it? The quantity 1 minus 1 half squared raised to 1 half is 1 all over, okay, 3/4 squared is equal to 16 over 3 positive. Okay, f prime of positive 1 half is 16 over 3, so it's increasing. Then f prime of 2, f prime of 2 will be 2 times 2 over 1 minus 2 squared. So 4 over 9 positive. F prime of 2 is equal to 4 over 9 and it's increasing. Okay, increasing. So let's evaluate. The values are, okay, from negative infinity to 1, the function is increasing, it's decreasing. From negative 1 to 0, still decreasing. From 0 to 1, increasing. And from negative 1 to infinity, decreasing. Now, let's look at the function values at our critical points. There is no function value, by the way, at x equal to 1 and negative 1. But there is a function value at x equal to 0. Okay? So, take note. There are no function values at x equal to 1 and x equal to negative 1 because the function is not defined on these x values. But there is a function value at x equal to, okay, but at x equal to 0, there is a function value, which is 0. Which is 0. Remember that the point 0, 0 is the x and at the same time the y-intercept from our step number 2. We now proceed to step number 6 then. Okay, number 6. calculate the second derivative. We now take the second derivative and check whether the graph will concave up or down at which particular intervals. So, f, nag-erase, calculate f double prime of x. F double prime of x. So, f prime of x from our previous step is 2x over, okay, 1 minus x squared squared. So, f prime of x therefore is, okay, the denominator 1 minus x squared squared times derivative of the numerator minus the numerator 2x times the derivative of this applying the generalized power rule. The derivative is 2 the exponent times 1 minus x squared, exponent minus 1 times derivative of the base, which is negative 2x, all over the square of the denominator, which is 1 minus x squared squared, or to the fourth power. Okay, when simplified. So, simplifying this further, f prime of x is equal to, we can simplify this by looking at factor. We can factor out 1, bakit nag-e-erase? Equal to the quantity 1 minus x squared, okay, times, we factor it out, times 2 minus, or 2 rather, times, may I erase this first? Okay, 2 times 1 minus x squared plus 8x squared when simplified. Okay, all over. Okay, but you can multiply this. You can multiply the 2, making it 1 minus x squared. 1 minus x squared to the fourth power. Okay, and when simplified, we can take note that we can cancel out this, and this one becomes 3. So, we could simplify it as 2 times 1 minus x squared plus 8x squared all over 1 minus x squared cubed. Or when simplified, 2, this one, 2x squared, negative 2x squared plus 8x squared will be 6x squared plus 2. So finally, we can reduce this into 6x squared plus 2 all over 1 minus x squared raised to the third power. So this is f double prime of x. Now we move on. First, we need to find the x values, x at which the second derivative will be 0. So next that we are to do, we set f prime prime of x to 0. Find all the values of x that will make the second derivative 0. So our second derivative from the previous step is 6x all over the quantity 1 minus x squared to the third power. Set it to 0. Okay? So, x squared plus 2 dapat. Going back, yan, x squared plus 2. X squared plus 2. Okay. Now, since our numerator, look, x squared. This is x squared, sorry. I did not copy very well. Going back, x squared. Will there ever be a value of x that will make this 0? None, because you will end up with 6x squared plus 2 equal to 0. and you'll end up with something which is imaginary, 6x squared equal to negative 2. So we say, okay, x squared plus 2 will never be equal to 0. So, and furthermore, f prime is not undefined for any x in the domain of f. So, but we discussed earlier that positive 1 and negative 1 are not in the domain of f. Therefore, to determine the concavity of the function, we simply divide the interval into the smaller intervals, negative. We divide. Take note that the function is not defined at x equal to 1 and x equal to negative 1. So we simply then divide the interval into negative 1, 1. So our intervals will simply be negative infinity to negative 1. Okay, 1, 1, negative 1, 1, and positive infinity, negative 1 to positive infinity. So let this be our intervals, because from here we cannot determine any x value that will make f double prime of x 0. It can never be 0 because we will end up with something which is a complex number or an imaginary number. So our intervals then, considering that the function is not defined at these two values of x, our intervals, we will look at the behavior of the function at to the left of negative 1, between negative 1 to 1, and positive 1 to infinity. So from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. Now we are to identify some test points. Test points, here let x be negative 2, let x be 0, and let x be 2. Now we will look into the sign of f prime prime of x. And then what will be our conclusion? Okay, sign of f prime prime of x. What is f double prime of negative 2? So, f prime prime from our previous step is, what did we get? 6x squared plus 2 all over 1 minus x squared to the third power. Okay? So, what will f prime prime of negative 2 be? F prime prime of negative 2 is equal to 6 times negative 2 squared plus 2 all over, 1 minus negative 2 squared to the third power. Okay, what will this be? Will this be positive or negative? So let's see. This is 24 plus 2, 26 all over, 1 minus 3, negative 27, correct? Also negative 2. So what can you say? Concave down. Okay? Concave down because it's negative. How about f prime prime of 0? F prime prime of 0, what will it be? Okay, f prime prime of 0 will be 6 times 0 squared plus 2 all over, 1 minus 0 squared raised to the third power, 2 over 3, positive. Okay, so this one is positive, and so this one concave up. Next, what is f prime prime of 2? F prime prime of 2, what will it be? So, 6 times 2 squared plus 2 all over 1 minus 2 squared to the third power. What will this be? 26 all over negative. This is negative 27. Negative. Okay? So, f double prime of 2 is negative. So, the graph will concave down. So, now let's try to draw the, combining all the information, we will now draw the graph. Okay? F changes concavity at x equal to negative 1 and positive 1. So, how would the graph look like? Okay, spin 1, 2, negative 1, negative 2. Okay, let's go back. What did we say? The function is not defined, so cannot possibly pass through with our horizontal asymptotes and vertical asymptotes. We begin with these two. Horizontal asymptotes. Step number 2, what did we say? We found out that the function has a horizontal asymptote at y equal to negative 1. So, let's draw that using dotted line or dash. Let me use blue. Y equal to negative 1 is this. Okay, y equal to negative 1. And what did we say about the vertical asymptotes? The function has two vertical asymptotes. And these are x equal to 1 and x equal to negative 1. So, let's draw these lines too. X equal to negative 1 is this. And x equal to positive 1 is this. Okay, what else do we know about the function? From step number 1, we found out that the function passes through the point 0, 0. So, it will pass through this 0, 0. Going back, step number 1. Oh no, it's here. Okay, so once more, let me underscore this is the horizontal asymptote. We drew that a while ago. And it passes through 0, 0. Okay. And the vertical asymptotes are okay. So now we are to look at step number 5. What did we say from step number 5? The graph from step number 5. Ayan. From negative 1 to infinity. From negative 1 to infinity, it's decreasing. Okay? Decreasing. From negative 1, okay, from negative 1 to 0, negative 1 to 0, it's decreasing. From 0 to 1, it's increasing. From 1 to infinity, it's also increasing. Okay, now let's go back. Go back to our graph. And from negative 1 to 1, from negative 1 to negative 1, it's concave downward. Okay, downward. From negative 1 to infinity, it concaves downward. Next, from negative 1 to positive 1, from negative 1 to positive 1, concave upward. Concaves upward. And from positive 1 to infinity, it concaves downward. So how will the graph then look like? Okay, so once more, if you take a value, it says here from negative infinity to negative 1, it is, go back, concave downward. Okay? Downward. From negative 1, lakihan. Can you see it? Nakikita. Nakikita naman nila eh. From negative 1 to positive 1, up.
Sundin mo yung size ng linya.
Sige, lakihan daw natin. Once more, let me write here na lang. From negative infinity to negative 1, down. Okay? From negative 1 to 1, up. From 1 to positive infinity, down. So, how would the graph look like? Now, we can begin from here. So, we can start with this. From negative 1 to 1, take note that the graph will never, cross this line. It will never cross this line because these are the asymptotes. It will only get closer and closer to these lines, but it will never touch this line. In like manner, if this is the horizontal asymptote, but na-erase. The graph will never intersect the horizontal asymptote, but it will get closer and closer to it. Okay, now how would the graph look like now? Let's begin from the middle. Ito muna. From negative 1 to 1. So from negative 1, this is that interval. From negative 1 to positive 1, it will concave up. Pataas, concave up. But it will pass through the point 0, 0. So how would the graph look like? Okay, so from 0 to negative 1, 0 to negative 1, it's increasing. Go back once again to step number 5. Okay, from negative 1 to infinity, see this? From negative 1 to infinity, it's decreasing. Decreasing. From negative infinity to negative 1, it's decreasing and it will pass through 0, 0. And then from negative 1 to 0, it's still decreasing. But the moment it reaches 0, 0 to positive 1, it increases. Look at this particular part. I want you to pay attention to this. From negative infinity to 1 to negative 1, from negative infinity to negative 1, decreasing. From negative 1 to 0, it's also decreasing. Okay, from 0 to 1, it's increasing. And from 1 to positive infinity, it's decreasing. But we only have one extreme value, and that is the point 0, 0. Okay? 0, 0, that's the only local maximum. Yun lang. Kasi x is not defined at, or the function is not defined at x equal to 1, and x is not also equal to positive 1. So, going back to our graph, negative 1 to 0, it's decreasing. Negative 1 to 0, it's decreasing. Okay? 0 to 1, it's increasing. Increasing, but this will never cross this line. Okay? It will never touch this line. How about the behavior of the function from negative infinity to negative 1? This is, okay, from what did we consider in our graph here? This is from the interval. We consider the interval negative 1 to 0 and from 0 to positive 1. From negative 1 to 0, what did we say? Decreasing. Okay? And from 0 to 0 to 1, it's increasing. And what did we say about 0, 0? That's the local mean. That's why the graph would look like this. From negative 1 moving 0, it's decreasing. And then from 0 to positive 1, it's increasing. How about when x, okay, what happens when x is from negative 1 to negative, or negative infinity to negative 1? You try with a point, okay? Here. So, let's take an x value. Let x be, let's say, negative 2. Where is this found? So, evaluate the function at negative 2. F of negative 2, what will that be? The original function given is, okay, go back to our original function. Our function is x squared, okay? So, 2 squared all over 1 minus 2 squared. From the original function, we are evaluating at negative 2. So, 2 squared. Okay, what will this be? 4 all over negative 3, correct? So, negative 2. So, if this is negative 2 and negative 1.3, something like that. So, somewhere here. Okay, somewhere here. Let's try a value very close to negative 1. Let's say negative 1.1. What about at x equal to, negative 1.1? What will f of negative 1.1 be? What will this be? Okay, so again, from the original function, negative 1.1 squared is 1.21 squared. Okay, so negative 0.21. Okay? And 1.21 divided by 0.21 is 5.76 negative. So where is that found? Somewhere here. Negative, let's say negative 4, negative 5, negative 6, negative 5.76 is somewhere here. So if we now draw this part of the graph, it would look like this. It will get closer and closer to this horizontal line, and it will also get closer and closer to the vertical line, but it will never touch that vertical line. It will never touch this vertical line. It will never also cross this horizontal line. Never. Okay? It will never cross that horizontal line. How about the next interval? So we're done with these two. Okay? So we have graph the function from negative 1 to 0, 0 to 1, from negative infinity to negative 1. How does the function behave from positive 1 to infinity? What about from positive 1 to infinity? Okay, so the next interval is from positive 1 to infinity. Let's identify x values. Let's say x is equal to 2 and x is equal to 5. What is f of 2? Our original function is x squared all over 1 minus x squared, 2 squared. What will this be? Okay, what will this be? It will be 4 over negative 3. Take note, it's also negative. Okay, 1.33. So, what about when x is equal to 5? F of 5 is equal to 5 squared all over 1 minus 5 squared equal to 25 over negative 24. Okay, so negative 1 point something. Okay, 25 divided by 24 is negative 1 point something, 1.04. Okay, so let's locate these points. Locate these points in the graph. Okay, 2, negative 1.33. So 2, negative 1.33 is somewhere here. Okay, how about the value which is very close to positive 1? Okay, why did we choose 5? Let me choose 1.1. Yung malapit na malapit kay 1 kasi hindi pwede si 1. Take note that the function is not defined when x is 1. So let's say 1.1. Palitan natin si 5. So if x is 1.1, what will the function be? F, okay, f of 1.1 is equal to 1.1 squared all over 1 minus 1.1 squared. What will this be? 1.21 all over negative 0.21. What is it equal to? The same as the previous. Okay? 1.21 divided by 0.21 is 5.70, negative 5.76. So take note that you will end up with the same x values. Tama. Okay, negative 5 point is somewhere here. So if we now draw the graph, it would be, okay, so your graph would try to get closer and closer to the horizontal asymptote, and it will also get closer and closer to the vertical asymptote. Okay, so this is the graph of the function. So the graph of the function would look like this. In fact, there are 3 parts of the graph. Okay, so from which interval? From negative infinity to 1 to negative 1. Ito. Correct. So that confirms, see that? That confirms our step number 6. That from negative infinity to negative 1, negative infinity to negative 1, ito yon. The graph concaves downward, while from negative 1 to positive 1, concaves upward. And from positive 1 to infinity, it concaves downward, pababa. Okay, now let's verify using GeoGebra. Okay, get your GeoGebra, or in your GeoGebra encode or input the function once again. The function, original function given is f of x is equal to x squared all over 1 minus x squared. Okay, let me check if I input the correct function. X squared over x minus 1, I should say. Okay, the original function given, our original function is x squared over 1 minus x squared. Sorry. 1 minus x squared. Okay, so compare. Now look at the function that is generated by GeoGebra and compare it to the function that we have just drawn. Are they the same? Are they equal? Are they the same? Okay, so see, the graph will never touch the line y equal to negative 1 because this is the vertical asymptote, or the horizontal asymptote rather, and these lines are the vertical asymptotes. Okay, so correct. Our graph is correct. Okay, so compare it here now. The same as the graph generated by GeoGebra. So how do we call this line? Once again, these are the vertical asymptotes, and this is the horizontal asymptote. How do we identify the vertical asymptotes? Check the denominator for values that will make it 0. And for sure, that will give the vertical asymptote. That is when the degree of the numerator is equal to the degree of the denominator. Otherwise, then you have to simplify the given. And the horizontal asymptote, How did we get the horizontal asymptote? Evaluate the limit of the function at infinity. And then test for points to the left and to the right or within your critical values or critical numbers. Okay, so this is how to sketch the graph of a rational function. Now we proceed then to the next. So this is it. So far we have already discussed some problems on optimization, on optimizing, maximizing area. For example, I gave one example on maximizing volume, maximizing the amount of material. Now, we did not discuss this yet. Maximizing revenue, surface area. Surface area related to that of the open top cylinder. Then minimize. So, optimization does not refer only to maximum. It also refers to minimizing cost. For example, if you are into business, okay, minimizing cost, minimizing travel time. Now, let me skip example number 3. I will just send, or should I say, upload the solutions na lang because we're lacking time. Ito na lang muna. We proceed to derivatives in rectilinear motion. And this is rather simple. Recall from physics that a body which moves in a straight line is said to be moving in a rectilinear motion, be it along the x-axis or horizontal or along the vertical axis, okay, or vertical. So it's either horizontal or vertical. We call that rectilinear motion. Straight line. Motion to the right, okay, ito yan. It's either motion to the right or forward, upward is positive. Okay? Motion to the left, backward, downward is negative. Okay? Your vector quantities in physics, your vector quantities like displacement and velocity, please take note of the signs. To the left, it's negative. Downwards is also negative. To the right is positive. Upward is also positive. Now, derivatives in rectilinear motion. Now, we have 2 or should I say 3 functions. Usually, it will provide, or a problem about rectilinear motion will provide the function position, which is usually S of t. S for position, t for time. Okay? S of t here, S of t gives the position at a specific time of travel. So, if I say, where is the body in 2 seconds? Then that means S of 2. Where is that moving object after 5 seconds? That's S of 5. So, S of t gives the position at a particular time. The position function of a moving body indicates how far the body is from a reference point, or referred to as the distance of the body from a reference point, denoted as S of t. Okay? T is time and S for distance traveled. Now, if S of t is provided, we can easily identify the velocity and acceleration. The first derivative of distance with time is the velocity. Take note that in physics, velocity is equal to rate of change of distance with time, di ba? Kilometer per hour, mile per hour, and so on. So, the first derivative then of distance with time is the velocity. So, you have to remember that. The velocity function is the change, rate of change of distance, okay, or position with time. V of t, or simply S prime of t. Okay, ito given, S of t. And how do we get the velocity? Differentiate, okay, with respect to time. Okay, S prime of t. And how about acceleration? Okay, acceleration is the rate at which the speed is increasing or decreasing, yes? So, which means the acceleration is the second derivative of distance with time, or the first derivative of velocity with time. Okay, so v prime of t gives the acceleration or the second derivative of s with respect to time. Okay, so velocity is simply s prime of t and acceleration is s double prime of t. Okay, rate of change of velocity of a moving body denoted as a of t. Okay, function is derivative of the velocity. Okay, and that's it. Second derivative of distance with time. Second derivative of the position function. Now let's look into example number 6. So see, look at this. The function s of t is given. It's always like this anyway. A body moves along a straight line, include the word line, according to the position function s of t. Let me copy now. Our position function s of t is equal to t cubed minus 9t squared plus 15t plus 3. For the time travel 0 to 3 seconds. Letter A, compute the position of the body after the following values of t. So the problem, letter A, ask for position. Okay, gaano na kalayo after 0 second, after 1. So, for A, we simply evaluate. Okay? So, simple evaluating the function at t equal to 0, t equal to 1, t equal to 2, t equal to 3. Kasi the problem ask for position lang naman, distansya. Nasaan na siya. So, for t equal to 0, then s of 0. Simple as that. Okay? So, for letter A, this asks for s of 0. Just evaluate. 0 cubed minus 9 times 0 squared plus 15 times 0 plus 3 is simply equal to 3 meters. Because that one is the unit provided in the problem. So, what about if it asks for position? All you have to do is to evaluate, okay, the function at t equal to blah, blah, and blah. Okay, whatever that t value is. At t equal to, let me leave it blank. For letter B, if it asks for velocity, okay, you only have to take s prime of t, the first derivative. So for letter B, s of t is equal to, okay, what's the function given? Our function is t cubed minus 9t squared. 9t squared plus 15t plus 3. So, s prime of t, that is now the velocity. Okay, so the velocity is equal to 3t squared minus 18t plus 15. So, if the problem asks for velocity after, okay, 1 second, for example, after 1 second or at 1 second, then you simply evaluate s prime of 1. And 3 times 1 squared minus 18 times 1 plus 15, s prime of 1 will be equal to, okay, 0. Okay, correct? That will be 0 because 3 plus 15. Okay, so it will be, it will come to a stop. Next. Ito naman is similar to the previous. Compute the position velocity. Just the same. So for letter A, it will be position at, let's say, isa na lang, at t equal to 2 will be s of 2. Okay? And our s of t is equal to negative 5t squared plus 25t. So all you have to do is to evaluate negative 5 times 2 squared plus 25 times 2. Okay, what will this be? This is equal to negative 20 plus 50 is equal to 30. And then if it asks for velocity, then s prime of t. S prime of t is equal to negative 10t squared plus 25. So if it's asked for velocity after, okay, after let's say 2 seconds, then it's simply s prime of 2, which is negative 10 times 2 squared plus 25, which is negative 40 plus 25, which is equal to negative 15. What is the unit? T seconds, meter per second. And for letter B, acceleration. Okay, for letter B, acceleration is simply the second derivative. So B will be s prime prime of t, which is equal to, okay, from here, differentiate, it's negative 20t. Okay, at any time t, it will be this will be the acceleration. Okay, so this is the acceleration. So it's simple. So for rectilinear motion, all you have to remember is s of t gives the position or distance from where it started. S prime of t is the speed or velocity. And s double prime of t is the acceleration. Last para matapos na natin ang differential at mag-integral na tayo. Okay, given the function z equal to xy, so in terms of two variables xy, the partial derivative of a given function can be obtained by differentiating the function, treating all other variables as constants. So if we have a function which is expressed in terms of two variables x and y, like z, in terms of the variables x and y, the derivative, okay, is called partial if we take only derivative with respect to x or with respect to y. Okay? And if we are differentiating with respect to x, treat all other variables as constants. In like manner, when we are differentiating with respect to y, treat all other variables as constants. This is rather easy also. So for example, if we have z, which is expressed in terms of the variable x and y, okay, we can take two partial derivatives here. One could be dz over dx or dz over dy. We can differentiate the function with respect to x or with respect to y. Now, if we differentiate with respect to x, then treat y as a constant. So, if we have then 4xy, the derivative of z with respect to x is equal to y is constant. Okay? So, treat y as a constant. So, what will this be? So, if this is a constant, derivative of 4x is 4 times the constant y, so 4y. Okay? Plus, derivative of 3x with respect to x, remember our variable of differentiation is x. So, derivative of 3x is 3. Okay? 3. And derivative of y, which is a constant, is 0. So, we have here derivative of z with respect to x, the partial derivative, this is how we denote it, the partial derivative of z with respect to x is 4y plus 3. How about if we differentiate it with respect to the variable y? Okay? So if it's the variable y, then we treat x as a constant naman. So alin naman dito ang constant kapag si y ang ito, constant, and then x also will be constant. So, the partial derivative of z with respect to y will be, okay, this is constant. So, derivative of y is 1 times 4x is 4x plus derivative of 3x, so 3x will be a constant. Derivative of a constant is 0. And derivative of y, okay, derivative of y with respect to y is 1. So, plus 1. Okay, plus 1. And that's it. There we have it. The partial derivative of z with respect to y is 4x plus 1. So, simple rule, if we differentiate with respect to the variable x, treat all other variables as constant. If we differentiate it with respect to the variable y, do the same thing. All other variables are treated as constants. Let's look at the last example. Find the partial derivative of, okay, of u equal to x squared plus y squared, x square root of y. Bakit na doble-doble? Ay, ilagay na lang natin dito. Okay, let u be equal to x squared, y squared plus, what the function given is? Okay, x square root of y. X square root of y. So, find the partial derivative of u with respect to x. Okay, so treat y as constant. Okay, because we are differentiating with the variable x. So, ito lang. Ito constant. Constant din yan. So, what will it be? Okay, derivative of x squared is 2x and then the constant y squared. Okay, plus derivative of x is 1 and the constant square root of y. Correct? So, let's check. Okay, correct. See this? 2x y squared plus the square root of y. How about when we differentiate with respect to y? Okay, what about du or the partial derivative of u with respect to y? So in our function x squared y squared plus x square root of y, this will be a constant. Okay, and this will be treated as constant. So, what will this be? Ito lang i-differentiate natin. Okay, derivative of y squared is 2y. Correct? 2y times the constant x squared plus derivative of y squared, square root of y, I should say. Note, square root of y is y raised to 1/2. So, its derivative will be 1/2. Okay, 1/2 y raised to negative 1/2 times the constant x. Okay, so the partial derivative of u with respect to y, therefore, is equal to 2x squared y, okay, plus x over 2 square root of y. Let's check. Okay, correct. 2x squared y plus x over 2 square root of y. So, I hope you understood what the partial derivatives are. So, we end up with this. I will just send, or if I could make a video on the